Three-wire leveling is another method of enhancing leveling accuracy. In this method, instead of reading the leveling stuff at the center here, we will also do readings at the top and the bottom. So instead of one measurement, we'll do three. Then we will average these three measurements, and this will enhance the leveling accuracy. For example, of course, we will do this at all the points. For example, for point A, we'll read the top, center, and the lower. Again, for point B, we'll do the same thing. We'll read the top and the center and the lower here. Now, one property of the telescope and the three hairs of the telescope is that there is a ratio between the horizontal distance and the distance between the crosshairs. So if you take the upper minus the lower readings and multiply it by what we call the multiplication factor, or sometimes we call it the constant of the telescope constant, and usually it is 100. So if you multiply the difference in readings of the leveling staff by the leveling constant, or the multiplication factor, this will give you the horizontal distance. For example, the horizontal distance A equals the difference between the top reading and the bottom reading multiplied by this constant, which is 100 in most cases. So I is the stadia spacing, which is the top minus the lower, and C is the multiplication or the telescope multiplier, and it's mostly 100. So basically what's happening in the three-wire leveling is that we have three readings, and these readings, they are at the top, lower, and the middle or center here. We take them, we average them, and then we use them in the backside and the foresight calculations, height of the instrument calculations, and finally the elevation of these points. And because we are doing more than one measurement, so this will enhance the accuracy of the leveling. Of course, reading to the closest millimeter, as usually we read the centimeters and then we estimate the millimeter reading. Of course, the leveling rod we are using should be always calibrated and checked for its integrity. At the end, completed loop or check into another benchmark of unknown elevation. We have to do the checking of the leveling loops. So the leveling notes is almost the same, except that we have more readings than the usual table, which is only the center here. So look, it's as simple as that. What do we have? We have readings at the backside, and then here we have at the backside, instead of 4 readings at the benchmark, we have 3 readings. So we have the upper, the center, and the lower. We add them together. This is the summation of the 3 readings. Then we average them by dividing them by 3. So this is the average. To further check, we said the difference between the upper reading and the lower reading should give you the multiplied by 100 should give you the distance between the level instrument and the point. So here is the same thing, except since we are reading the top, center, and the lower, we will take a difference between the upper reading and the center reading. This should give you half the distance, which is this part. And then we take the center to the lower, and this is another half. So we calculate the upper half, the one half, and the other half, and then we add them together to get the total distance between the level instrument and the point, and the leveling staff at the point, at the backside point on the benchmark. Here we have to be careful that this is a good method if you want to check if you are having blunders or making blunders during the readings. If you have a great difference between this half and this half, that means you have something wrong. Theoretically, when you read the top, the center, and the lower, you should not be having a difference in the distance by that much. If you have like a noticeable difference, that means you have something wrong. You have to repeat the reading. The same thing, we do it when we go to the foresight reading. So foresight point, we'll take the, again, upper, center, and the lower. We add them together, and then we average them. Notice the negative sign here. We'll talk about it in a bit. But again, we would use the upper and the center to calculate the first half of the distance, and then the center to the lower and calculate the other half of the distance. We check that they are almost equal, and then we have to add them together to get the other distance between here and here. So what do we have also in the notes? This is the elevation of the benchmark. Elevation of the benchmark given, and now if you remember, we have the height of the instrument usually equals to the elevation of the benchmark plus the backside, and here instead of backside we have the average backside, so let's call it average. And then we used to say the elevation of point X, which is the foresight, this equals elevation of the point equals the height of the instrument minus the foresight. So the foresight is actually negative, or it is subtracted. So here the same thing. When you take 5 point, this one which is the average, 5.2, and you divide it by 3, it will give you 1.6733. But in the notes there is this convention is that because later on we will subtract the foresight average, we would just give it a negative sign, and then we will summarize like at the elevation column here. The summary is that we have the elevation of the point. We have, this is the average foresight backside, the average backside, which is this one, which we will add it. So if you want to replace HI here, it will be elevation of the point of the foresight point equals, it is the elevation of the benchmark. We just substituting the HI values from here plus the backside average minus the foresight average. And that's why we have the foresight here as a negative value and the foresight is a positive value. So we take the benchmark, the elevation of the benchmark, add to it the foresight, the backside average, and this will give you, this is the interim, or let's say temporary summation after adding the backside average to the elevation of the point, and then we will take this temporary summation and we subtract from it the foresight reading, and this will give me the whole or the final elevation of the benchmark at the foresight reading. If you want to go further for a complete example, this is a very nice example on YouTube. You can just click the link and watch that video. This is a complete example. The one I think you will see very similar thing in the video in the previous slide. So you start from benchmark 17, you measure 3 values, which we just saw in the previous example. This is the summation, this is the backside average, and these are the distances. If you see, it is 10.0 meters, 9.90 meters, so the difference is just 10 centimeters, and the summation is 19.90. In a precise leveling, we always try to position the leveling, the level instrument in the center between the backside and the foresight. As you can see here, the distance between the backside and the instrument was 19.9, while the distance between the instrument and the foresight was 20.3, which is logically or practically this is perfect in the center. Again, we said this is the elevation of the benchmark. You add the average backside, you find the summation, then you take the which is the height of the instrument. Actually, when you add the backside and the elevation of the point, this is the height of the instrument, and then the height of the instrument, you will subtract the foresight average from the upper, center, and the lower summation, then average it is negative because we want to subtract it from the height of the instrument. At the end, this is the average height of foresight reading, and finally this is the elevation of point, turning point 1. From turning point 1, we take another backside to 3 readings, summation, average, and then we check the distances also. It's 25.4, 26, which is the difference is 60 centimeters. That's absolutely acceptable. But here you also notice 12.7 and 12.7, which means the readings at the top, lower, and upper, and the center, they were just very nice readings. Half of the distance is 13, the other half is 13, and summation is 26. So the same thing. We take the TP1 elevation that we just found, and then we add to it the average back size, and this will give you the height of the instrument in position number 2. This is in position number 1. Subtract the average 4 site readings, and this is the elevation of turning point 1, and then we continue. At the end, you have to do the arithmetic check like we did in survey. So for now, this is what we have for the 3-wire leveling, which is another method of enhancing leveling accuracy. Here, we did not rely on one reading on the leveling staff. We did 3 and we averaged them. As the measurements increase, we have redundancy, so the average will be having the most probability to happen in this case. And this is the basic principle of 3-wire leveling.